why do we care so much about reliability? Because typically companies, their press releases always state only the efficiencies, the same with heterojunction, Topcon, and with tandem. But typically the degradation rate is not mentioned. And these are not standard EL images. So normally for EL, dark is bad, bright is good. In this case, it's series resistance, and bright is bad and dark is good. So we see that after damp heat testing of only 6 hours. So then I'm also not only the bearer of bad news, but also some good news, and some good news for heterojunction and Topcon. For heterojunction, we actually showed that the application of barrier layers, and this is something we both published and patented, the use of aluminum oxide barrier layers can make the heterojunction solar cell stable against all the 4 failure modes.
As people start to trickle in, I'm going to walk through our agenda, our format, and of course introduce our illustrious guests. All right, let's jump into it. So this webinar, like most of our webinars, is going to be an hour-long format. Going to be talking for about 5 minutes now, and then we're going to let our panelists speak for about 40 minutes. And then at the end, we always like to leave around 15 minutes for Q&A. I will note that while the speakers are talking, you can send your questions into chat, and I'll be reading and monitoring them and have those ready before the conversation is over. So I'll look forward to that. The first of our guests is Professor Bram Hoeks. Welcome back. Thank you so much for joining us again. Professor Hoeks is a researcher and professor, deputy head of school at University of South Wales. He leads a research group that does nanoscale thin film photovoltaics research. They focus on performance, stability, and financial viability of those cells. He, in that research, has published over 250 papers, which is a wild number. And he's been recognized in that with international awards, as well as being featured in Solar 40 Under 40 by Renewable Energy World. So thank you so much for returning. We look forward to your talk. Next is Niklaus Weimar, who is our own CTO and co-founder at Sinovoltaics. He has over 15 years of experience in the PV world, 10 years physically living in Asia, conducting these research and audits of over 100 different facilities. In this research, this has given him the insights required to develop innovative solutions that are used at Sinovoltaics that give us the edge in quality control, such as SELMA, which we will speak about more later. So thank you to you, Nicholas, as well, for joining us. Lastly, I will do a brief introduction on myself. My name is Ryland Gordon. I'm the Director of Business Development for Sinovoltaics based in the United States. My academic background is in thin film solar cell fabrication. I focus specifically on material composition, deposition environments, and material cost to optimize efficiency and price. Then I jumped into the EPC space. I'm based in Atlanta, so most of our projects were on the East Coast. And now I'm working as the Director of Business Development for Sinovoltaics, again in the US. So if you have any projects deployed in the US, then I will be your main point of contact, and we'll be talking more. Also, along the lines of US development and manufacturing, we also put out our supply chain map today. So go give that a look if you have not so far. All right, without further ado, I will hand the mic over to Niklaus to start the discussion, and then we will get things rolling. Nick?
Yeah, thank you, Ryan, for your great introduction. And also again from my side, a very warm welcome to today's webinar, in which we look at the latest quality trends and related failure risk research findings when it comes to Topcon and HJT modules. Allow me to briefly present to you our team's latest quality observations regarding N-type Topcon PV module inspections from the mass production at the PV factories in Asia. When we look at the recent 6 months of 2024, we can see that many PV module makers have already switched to manufacturing N-type TOPCon modules, and so have also more and more project developers embarked on TOPCon module purchases. And while the share of the hesitating buyers sticking with established stable technologies of PERC modules becomes more and more small. Nevertheless, there is doubts and questions that remain about the long-term quality outlook of N-type TOPCon, and there is a substantial demand for targeted quality assurance and also reliability testing when it comes to these new modules. And this is also why certainly a deeper scientific understanding on this subject, in which Professor Hoeks from UNSW are leading researchers, and it's so crucial for both developers and manufacturers alike. So with the increasing volumes of N-type TOPCon modules taken up by project developers, we also have, of course, now more and more related quality data that we can share today, and also, of course, like the trends that our team observed doing the quality assurance work at the factories. So one noticeable trend is the actually decreasing rework rate across many, yet not all N-type TOPCon makers. In this slide, you can see recent average pre-lamination rework rates at 3 different manufacturing facilities from 3 different suppliers, with data that cover Q1 2024 from January to March. As you can see, the percentage of pre-lamination reworks on PV modules is going down for 2 of these factories exemplified here. And these factories have, in this regard, implemented improvements in the raw material handling, processes setups, and also calibration of equipment, and also, of course, improved their understanding of N-type TOPCon and related failure risk or quality risk. So for example, for facility A, the average rework rate went down from about 15.45% in January to 8.35% in March 2024, while for facility C, it went down from 7.73% to 3.36% in March. In both cases, this is a remarkable improvement. And in this trend development, main cell level defects identified with these modules and thus subjecting them to the reworks were nowadays mostly solder issues or issues basically on the performance on the cell edges, and various types of microcracks, and to a lesser degree cell positioning issues. Obviously, manufacturers are improving their understanding about TOPCon, and of support in this learning process have also been the findings of our quality engineers, in particular brought by the usage of our proprietary AI-based software Selma, which allows us at Sinovoltaics to perform 100% image analysis, and of course then a vast amount of quality data that we can access. And so Selma has in this regard actually provided here important insights and a grasp of the extent actually of quality issues that need to be addressed. Now, furthermore, we can see significant differences also in coping with N-type TOPCon quality issues across the different production facilities of the same supplier as well. So I have here a quick recap here from our previous webinar with Professor Hoeks. Back then, we saw that at facility A of manufacturer A, so it's one facility of the manufacturer we are going to speak about. So the rework rate went down from 16.16% to over the total of 2022 to 4.91% in Q1 2023. So how does this facility A compared to its peers from the same supplier in this year, or the first quarter of this year. We can see here that for facility A, the average pre-lamination rework rate in Q1 2024 has now further dropped to below 1.5%. Meanwhile, the rates are much higher at other facilities, some of which with a falling trend, and some of which with an up and down trend. So facility B, for example, started off at about 9.3% of a rework rate in January 24, dropped to 7.42% in February, and then up again at about 9.6% in March. This is also an indicator that the experience and handling level with N-type Topcon modules at different production facilities of one and the same supplier can be quite different as well. So choosing the right facility is of importance, of course. And boosting such experience and handling level can help to bring about vast improvements, and here necessitates the support and insights from science, which brings us now to the presentation of Professor Bram Hoeks today.
Thank you, Nicholas and Roland, for the kind introduction, and thanks for having me back to present some of our latest insights on Topcon and heterojunction reliability. So I'm Bram Hoeks, a professor at the University of New South Wales of the School of Photovoltaic and Renewable Energy Engineering. It's actually started 50 years ago when Martin Green started PV research at our university. And it started with one person, but now it has expanded into 200 people working on renewables, mostly on photovoltaics. And we have 22 shared labs, and we have a whole range of professors working often together in projects to solve the challenges, because it's always multifaceted. And we train a lot of students. We currently have 450 students in our school. We have quite a wide range in PV research. I will not go through all the detail, but we work on developing, we call it enabling technologies, which are building blocks either for characterization or solutions that can be applied at a wide range of solar cells. And then we study all the relevant industrial solar cells are there at the moment. So it's also the topic of my talk. And also we work on all the tandem-based solutions that are out there. So not just silicon perovskite tandem. We work on all of them, and for that we have an intimate knowledge of the pros and cons of these technologies, which will help us to support our clients. So this presentation, I will mainly talk about module and cell reliability. So why do we care so much about reliability? Because typically companies, their press releases always state only the efficiencies, the same with heterojunction Topcon and with tandem, but typically the degradation rate is not mentioned. And from this graph on the left, you can see that if your degradation rate is high, and which is still the case for silicon perovskite tandem, your high efficiency, that benefit that you have will be completely eroded by the degradation rate in terms of LCOE, so levelized cost of electricity. So if you plan to run your farm for 25 or 35 years, a low degradation rate is key. We really need to have that. And it also shown on the right that if you look at LCOE, you can actually afford to pay a little bit more if you can if it means your modules are more stable. So the topic of today's presentation is heterojunction and Topcon, and these are some results which are a few years old, but basically they sparked our research. So this was a damp heat test on a glass backsheet heterojunction module. So most heterojunction modules are glass, But of course, if you want to save costs, you want to go to cheaper encapsulants and to backsheets, and their modules are also lighter. And we identified four new failure modes in these modules, which were not seen with PERC. And we were not able to reproduce them at the cell level. So these were really some new failure modes that we had to investigate a bit deeper. So I will show that in some of the next slides. And then for Topcon, and this is work presented by JE Solar last year at the EU PVSec, where they showed for Topcon, even with glass, if you, in that case, they tried to move to an EVA stack, and they saw that after 3,000 hours of damp heat, there was significant degradation coming in from the edges. So basically where moisture can enter the module, because these modules do not have edge sealants, we saw degradation. They also showed that if you put EPE on the front, which is a mixture of PUE and EVA, then actually the loss is down to a respectable level. So that's a way to get the module more stable. And then if you want to go to glass backsheet, it was basically, even with using PUE, the module showed a degradation rate, which we can see on the left, that was above 7% after only 2,000 hours. And then they showed that if you overlap the cells, which basically makes it harder for the moisture coming through the backsheet to reach the front of the cell, then the loss was a little bit lower, but I would still say uncomfortably high. And this gives an indication already, this results that the front of the Topcon may be one of the main issues, and that I will show that in the rest of the presentation. So then they showed that if you use the right so basically, even if you use this overlapping technology and then go to a cheaper encapsulant, yeah, you can still have too high degradation, and it's basically, in this case, spread throughout the whole module. So there's still some work to be done, and this was only published last year by one of the leading tier 1 manufacturers. So the remainder of my presentation, I will go into detail on some basically these new failure modes. So we've identified 4 new failure modes in heterojunction 3 and Topcon. I will show that some of them actually can be sparked by the combination of the bill of materials. But fortunately, I also have some good news that a lot of these degradation modes can actually be fixed at the cell level, which is, in our view, the safest way to do it. If your cell is more intrinsically stable, it gives you more leeway in your encapsulant and your backsheets. And then finally, I will show you some of the approaches we're taking to take this to the yield level, because that's, of course, what all of you want to know. So all these, are these degradation modes only of academic interest, or how much are they going to hurt us at the field level? So first, this work we published last year, and it was also, I think, discussed it in my last seminar, but it's good to repeat it because there's some similarities between Topcon and heterojunctions here. So this is for heterojunction, where we identified 4 new failure modes. So we called type 1, where we have localized failures popping up in electroluminescence. So both images here are electroluminescence images. Type 2 and type 3 are failure modes that starts from the bus bar, so where the soldering takes place, and then if it spreads out, it can basically take out the metallization in between the bus bars. And type 4 is, we call it bus bar darkening, and we typically see that when EVA uses the bill of materials. So you can see that the degradations can be quite significant. So we see losses up to 50% for heterojunction only after 1,000 hours, if type 3 really goes into overdrive. But also the other losses are beyond what we would expect. So the good thing is that we were able to reproduce all these failures at the cell level. So cell level testing has a number of advantages. It's typically 10 to 100 times quicker. So we get feedback typically in 20 hours. So in one day, you know, the relative sensitivity of your cell. And also it allows us to do more characterization, so to understand the fundamentals. And I think that this is still a very important function we can, as a university, can provide to the industries, to understand these failure modes. And once you understand them, you can actually solve them a lot quicker. So if we look at type 1, it's basically related to contamination. So if you're a vertically integrated manufacturer with cell and module manufacturing in one facility, clean room facility, this will typically not be a major issue, although we have picked up some contamination of handlers. So we sometimes see handling marks popping up after damp heat testing, which is also a type 1 failure. So, but this is a major concern if you're a module manufacturer buying in cells and you're not operating a module line in a clean environment. The type 2 and type 3 are related to soldering flux. So if you use the wrong soldering flux, that can have quite an aggressive reaction with your metallization and even with your ITO, so with your transparent conductive oxide. And there's a lot of changes happening in the ITO. We want to move away from indium, and this typically makes the TCO, the transparent conductive oxide, even more sensitive. So this is something we definitely have our eye on. And then the fourth one is when you have acetic acid formation, then you get this busbar darkening. So the next one we look into is sodium. And this basically was inspired by work presented by EPFL just 2 years ago at the World Solar Conference, where they showed heterojunction solar cells. This was glass, but with a poor edge sealant. And they saw significant degradation after 2,000 hours of damp heat testing, which they related to sodium. Then this work was from TNO, so on the right, where they showed for Topcon solar cells, and this is a bit of confusing result. So the blue line shows that when you have the glass EVA stack, so you have significant degradation. If they left the glass off, so just at the EVA, the module was actually stable in damp heat. They related that to acetic acid formation, but glass is, of course, a common sodium source, so it could also be sodium. So that basically sparked us to look into, in a bit more detail, into sodium for heterojunction and Topcon solar cells. Because where is sodium coming from in your module? It's basically almost in every component that you use. All the glass has significant amounts of sodium, so it can be like 1% or more. We haven't tested a single encapsulant that doesn't have significant amounts of sodium. And then, of course, we have the well-known PID, where sodium from the glass is migrating to the solar cell. And then EPFL showed, and that's on the bottom left, where water comes in locally via the edges, and during its migration, it actually leaches off sodium from the glass, and in that way transports it to the cell. So and these failure modes take quite a while to go, so both PID and the leaching. So sodium gets to your solar cell eventually, or it's already there. So what we did was basically expose 3 types of solar cells, so PERC, Topcon, and heterojunction, purposely to sodium chloride. So we just use a salt solution. We sprayed it on the front, the back, or both sides of the solar cell, and then put the solar cell in damp heat testing. So it's quite an aggressive test, but I will show you that it's quite an effective test to qualify the relative sensitivity of your solar cells. So if we look at the differences between Topcon, heterojunction, and PERC, we see that Topcon is super sensitive if the salt solution is applied on the front. And this work was done 2 years ago. This was done before laser-assisted firing or LECO came into place, and that actually changes the results for Topcon quite a bit, as I will show later. For heterojunction, we see that both the front and the rear side are sensitive with losses, well above 20%, up to 50% if we apply it on both sides. And for PERC, we mainly see a sensitivity on the rear. And then I'll just show the rest of the IV results as well. And the only thing we have to look at here, that basically the main problem is the metallization, because we have the main problem is series resistance, and all the other solar cell parameters that are affected are dwarfed by the effect we see to series resistance. So that's why we focus the rest of our research on the metallization and the impact of sodium on that. And that is also further confirmed by these series resistance images. So these are not standard EL images. So normally for EL, dark is bad, bright is good. In this case, it's series resistance, and bright is bad and dark is good. So we see that after damp heat testing of only 6 hours for a PERC cell, that we see significant increase at the rear, when sodium chloride is applied at the rear. But then if we look at Topcon, basically our method is loses its validity. So we go outside of the range that we can measure if we apply sodium chloride on the front. And the rear is remarkably stable for Topcon in this test. For heterojunction, we see that both the front and the rear are sensitive, and this is just confirms that that it is a series resistance issue. It's highly uniform, because basically the non-uniformities that we see is just due to the application of our sources. But we also see, if we compare the two, so Topcon and heterojunction, we see that these failures look quite different, and that gives us some additional information in studying these degradation mechanisms. So in the next step, we looked at the contact resistance, because the series resistance, it's mainly driven by two components. So it's the line resistance. So are we affecting the whole metallization, or are we mainly affecting the contact between silicon and the metal, or the TCO? And that's basically, that was the case. So for heterojunction, we see a significant material increase, so like an order of magnitude for in the contact resistance on the front and the rear. But in particular for the Topcon solar cell, we see that contact is almost completely compromised. So the contact between silicon and the metallization is almost lost. So that's 2 orders of magnitude, and that explains the full drop in series resistance. And then we started looking deeper into that, and we looked at cross-sectional SEM images, so scanning electron microscope. If we then look at PERC, we see that the front, that contact before and after testing, it looks the same, but the rear contact is heavily corroded actually, but because of the PERC's unique structure, where we have aluminum alloying with silicon in the process, this part of the solar cell is actually not affected by this corrosion. So even though the outer layers is corroded, it's not affecting the series resistance as much. So still the contact with silicon is there, because it's just alloyed in. But it's the first indication that aluminium could be a problem here in terms of sensitivity. If we look at heterojunction, we see that both the front and rear contact undergo significant changes, and this is something we're still trying to get to the bottom of this. Our current understanding is that like the silver particles, particularly the small ones, are actually they're being removed, and they're basically they result in larger silver particles after this test. But this removal of these small particles, they're put in there for a purpose that actually compromises the contact with the silicon, and we can even see these contacts delaminating. So the adhesion of this contact is severely compromised by the reaction with the sodium chloride in this case, and that explains the significant increase in series resistance. But as mentioned, we're going into we're getting deeper into the chemistry there, and there will be work published on that in a couple of months. If we look at Topcon, we see that the rear is very stable, similar as PERC front. But we see that the front of the Topcon again has this very strong reaction, and we see this delamination again on the bottom. But we see that the main reaction is with these aluminum particles. So the Topcon, so pre-laser assisted firing, there was significant amount of aluminium in the contacts, like 3% we see for typical paste. And this is added in the form of little particles. But these particles, they're actually very reactive, and they're basically fully corroded away by the sodium chloride. And the sodium chloride also interacts with the lead oxide. And that's still something we see. These contaminants reduce the lead oxide to lead, and lead oxide is a key component in the contact formation. So the one problem is now solved with laser assisted firing by the removal of aluminium, but still the lead oxide is a sensitive point. So if we then look at into more detail into soldering flux, we see that is super sensitive, in particular for heterojunction. And this is some new results that we haven't published yet. So this is something we will be presenting at the EU PVSec in Vienna in September. We show here that we test just soldering flux applied onto a heterojunction solar cell, but actually in dry conditions. So we basically make the air as dry as possible, and we see that for certain soldering fluxes, the reactions are quite severe. So a significant increase in the series resistance here. So these are series resistance images again, and that's an important observation. So we don't need moisture to come in to be part of the chemical reaction. So the soldering flux by itself or the soldering flux residues by itself are sufficient to cause this degradation, which is consistent with the work we published earlier, where we saw significant degradations if the wrong soldering flux was used for heterojunction. So this is an important new observation that we have made in our labs. So soldering flux critical for your heterojunction to select the right soldering flux. So if we look at Topcon, so Topcon, we did not see any reaction in dry conditions, but if we add moisture, Topcon is sensitive. So we see that first, and it depends on the type of soldering flux you use, but you get significant, and these are EL images, where we see that and the solar cell shows it's not a significant Pmax loss, but so only 1%, but we see that so Topcon is sensitive to certain soldering fluxes. However, water is needed as part of the chemical reaction in order to get this sensitivity. So that's a significant difference between the two technologies. So here, heterojunction is more sensitive than Topcon. So then this is some of the latest work we published, and that created quite a stir in the industry, where we looked at the impact of the bill of materials on Topcon solar cells, because we use PERC as a reference. These modules were made at an industrial production line. These were not made at UNSW. These were made at a company that is producing hundreds of megawatts of solar cells. So they have very well-defined procedures, and we just were helping them in order of their material selection. So we tested a few BOMs for PERC, but the main focus was on Topcon, where we used 3 types of PUE, 1 EVA, and 3 types of backsheets. And we just made many modules and did damp heat testing at UNSW. For PERC, the results were, as expected. Basically, all the bill of materials were found to be stable that we tested. This was just basically to ensure that, we were comparing apples to apples. So basically, the production process was, this factory was running PERC normally. So they were well dialed in for PERC, so no issues there. Any drop in efficiency that we saw was mainly due to series resistance. So in purple again, so again consistent with the fact that metallization is the first attack in terms of damp heat testing. And then if we look at EL images, of course, these are mini modules, so there's a bit more handling there. So we see a few imperfections, but the main message from this slide is these imperfections are not changing after damp heat testing, which is quite different from Topcon, as I will show you later. So even if you have a little issue in PERC, it doesn't grow further, so it will be stable in the field as well. If we look at the results for Topcon, we see that the drops were significantly higher. So there was only a few bill of materials that were within the acceptable range, but the most remarkable result was for 6 and 7, where we tested PUE front back, and with 2 types of backsheets where we saw a significant drop in efficiency. So in this case, it was really the encapsulant which seemed to cause the degradation here. And then all the efficiency loss that we had was again in purple in RS, because even the green bar that we see there, the drop in current, it's basically because the metallization is so compromised that we cannot get the current out. So it's a metallization issue. If we then look at the EL images, they look quite different from PERC, and we have a few important observations here. So we see features that look quite similar to what we've seen previously with heterojunction, and I will show that in the next slide. But we also see, for example, in group 2, that we have these type 1 failures, so basically these point defects that are actually growing during damp heat testing. So that's a bit worrying. So that for Topcon, if you make a mistake in lamination, then this can actually spread after damp heat testing. And you see the losses for the worst modules. So on the right, they look quite similar to what we saw with heterojunction. So we basically saw 3 types of failures, which very similar to heterojunction. So we call them type 1. So type 2, which was the old type 4 for heterojunction, and type 3, because basically we ranked them in order of severance. And then if we look into the comparison of heterojunction and Topcon, we see the nice similarities. So we see here, so heterojunction point type failures that develop during damp heat testing, which we relate to contamination, and these were made at a different production line. So in different industrial production line, but still the same signature. So that is consistent with the fact that this is a more widely applicable concern. So basically, if you bake in contaminants in your laminated stack, then they will eventually develop in damp heat testing. And one of them could be handling marks, although for most companies this will not happen. But for example, if you have fingerprints, fingerprints contain like a significant part of the periodic table. But this is the one we tested before, sodium chloride. And when we tested some of the filled heterojunction solar cells that filled with type 1, we actually saw that there was a correlation with a significant amount of sodium in the degraded area. So it was, for that cell, it was a sodium-related contaminant. And we showed that proper cleaning may be applicable for heterojunction solar cells if you're not completely sure if your supply chain is clean. So if we look at this type 2 failure, so that's busbar darkening, which we saw mainly in the stacks where EVA was used, but also in some cases we saw it when PUE was used for Topcon. So that's still something we're investigating, but this degradation seems to be limited to the busbars and doesn't really spread out. And then in terms of failure mode, we believe it's probably because it's at the busbar. So soldering flux is of course locally applied there, and then In some cases, it's the acetic acid. So with EVA, acetic acid is formed, and those two could be part of the chemical reaction. But we're still working on this to fully understand this failure. And then if you look at type 3, that's basically that must be a reaction with so basically something that's in your encapsulant. So in the PUE, there's all kind of additives being used because the companies are trying to, for example, change the UV absorptions, and like it might be proprietary additives, and some of these additives are very reactive with the paste, and that's when you basically get this kind of failure, or if you have a reaction with the TCO as well. So that's why for Topcon we believe that that's more the additives that we should be worried about, the additives in the encapsulant. And this if you have this issue, that's really a significant concern. So then you can get degradations after so 50% after 1,000 hours of damp heat. The good thing is that as I showed you, these failures you can pick up with damp heat testing. So if you just do your check your supply chain on a regular basis with damp heat testing, so 1,000, 2,000 hours, you will pick up these issues. So then I'm also not only the bearer of bad news, but also some good news, and some good news for heterojunction and Topcon. For heterojunction, we actually showed that the application of barrier layers, and this is something we both published and patented, the use of aluminum oxide barrier layers can make the heterojunction solar cell stable against all the 4 failure modes, which is great. So you can make your solar cell intrinsically stable, so which makes your product more robust, but it also would allow you to study alternative bill of materials. Alternative means typically cheaper. And we see that in the series resistance imaging as well, that we still have some optimization to do, but this is a very aggressive test. And we only see, after application of the barrier layers, there's only a little bit of increase in the series resistance, but these cells are significantly more stable than that they were before. And it's just a 5 nanometer Alox layer applied on the solar cell. So then for Topcon, we had basically the whole industry in China now changing to laser-assisted firing, also called LECO, or our partner Jollywood calls it Jollywood Special Injected Metallization, but it's basically it's a laser-assisted firing where the main benefit is the main driver was the efficiency increase, but we showed that because you can now use aluminum-free paste, this significantly reduces its sensitivity to corrosion. So in the same test where we showed 92% power reduction for the standard baseline paste, we only showed 3.6% when they're using aluminum-free paste. So that's a significant improvement. And then we also we made modules as well, and we're still testing them at the moment. But after 1,000 hours, the results with the identical bill of materials was remarkable. So with the laser-assisted firing, only 2% reduction, and with the baseline, it was 7.3%. So this laser-assisted firing is a game changer, not only in terms of efficiency improvement, but by the fact that it allows for paste which are less corrosion sensitive. So we're very excited about this, and this is a big impact for the Topcon reliability. So the last part, I will go a bit quicker there. Because we're mainly presenting a framework, because what we want to do is relate these cell level testing and module stress testing to field performance. And there is still a lot of work to do, because you see all the kind of stress factors you have on the left that can result to failures in the field. And then if we then look at the work that has already been done in that area, it shows that having a linear degradation rate that is applied all over the globe is probably not the proper way to do it, because we see that, and I'm not sure, I think this probably was the thermal degradation rate they showed on the bottom, where it shows that in some parts of the world, the degradation would be significantly higher than, for example, in Europe or most of the United States. Particularly in Australia as well, some parts where we actually have the biggest plants for solar installation, they actually have the highest degradation. So this is something we have to take into account. That can be a factor 2 or 3. And so the main thing you have to look at is the stressors and how are they geographically distributed. So temperature, it's quite well known. So for example, in Florida and Atlanta, it's a lot warmer than in Portland or Seattle. So that would be a big difference. And that in terms of thermal degradation, that's a factor of 2 for the US easily. Relative humidity, of course, the tropics, very hot and humid. And then UV, there's also quite a significant difference over the whole world. So that's something we have to take into account. And that's basically what we can do for a modeling for every failure mode. We can come up, we calibrate basically the first principles equations, and then we can calculate what it is for your specific location. And that could mean that if you want to field solar cells, for example, in Indonesia or in South America, that you would have to use a more conservative bill of materials in order to maintain the same warranty. And the same with, this is encapsulant degradation. And this is, for example, the result for our work on thermal results, where it shows like degradation can be really orders of magnitude quicker if you look at it for over the whole year or of the whole plant lifetime than for example in Europe, where most of the standards, IC standards, are based on European conditions. So that's something, European or US conditions, where we see that they're actually more friendly to modules than the significant parts of the world. So that's something we have to take into account. And basically, we want to do this for all failure modes that I've discussed earlier as well. But that's still a little bit of work to do. So to conclude, I show you that a lot of the work that we do is developing cell-level testing for these new failure modes, which allows us to test not only quicker, but also to look at the first of the fundamentals, which will help us to understand the failure modes, and then we can help you basically to understand how to solve this failure or how important this failure is. We identified a couple of new failure modes for heterojunction and Topcon, which have unique fingerprints, and we related them to the most likely root causes, which can help you in solving these issues if you pick them up. A big part is sodium. Sodium, it's because it's a common contaminant. It's almost impossible to avoid. So you will typically end up with it in your module. And then the latter part of the presentation showed that the bill of materials, particularly the encapsulant and the additives being used, can have a significant impact. And this is important to know. So check with your suppliers. If they make any changes in the additives, you have to know, and you have to test if it affects your reliability. The good news is as well that so Topcon is more stable with laser-assisted firing if you use aluminum-free paste. And for heterojunction, there is a way to make them stable as well. But most importantly, if you select the right bill of materials, heterojunction and Topcon will be stable. It's just the technologies are significantly more sensitive than PERC. So you cannot just do the same thing you did for PERC. You have to be a bit more mindful. And now I'll show you the last part is that so degradation is not the same over the whole planet. So if you're looking at installations in hot and humid conditions, then you might want to be more conservative for your bill of materials. And we're always keen to work with industry partners to improve the reliability. We have already a couple of partners, including Canadian Solar, with who we did most of the work that we presented today. But we work with a number of the tier 1 manufacturers to understand their degradation better and to make their modules more stable. And I'm keen to work with many of you as well. Thank you for your time.
All right, thank you, Professor. It's super insightful. We will jump into some Q&A. We have just over 10 minutes left, and we have some good questions. So I'll just jump right in. Many of these are for Professor Hoeks, as you just dropped some really intense knowledge. So here they come.
Yeah, sorry for that.
All right, we'll start with. No, you're good. You're good. That's why we keep on inviting you back. All right, so the first question is, DH3000 is equivalent to how many operating years, and do you recommend it?
I wouldn't know out of the top of my head how many. It will be position dependent as well. I would definitely recommend it to do it because we see a lot of failures only popping up after like 3,000 to 5,000 hours. So all the top companies, so including SunPower, Maxion, who have been a reliability leader and are a reliability leader, they've been pushing that for quite a while. So I'm definitely definitely a fan of doing that, because some failure modes, unfortunately, they're not linear, they escalate. So that's also partly how the solar cell works, that initially you're not sensitive to this degradation mode with the same relative, even if that failure mode is increasing linearly, the impact on performance is not linear, so you can fall off a cliff, and that's something you want to pick up. So I would definitely recommend doing that for your internal quality control. Yeah. And
just to kind of piggyback on that, is that non-linearity specific to these Topcon and PERC as well, or is it kind of across the board?
No, it would be for every solar cell. It's some are related to the fundamentals of the solar cell. So like if you have degradation, additional surface recombination, for example, which is an issue with UV, which I haven't touched upon because we're still working on getting a clear picture on that. But even if you for a typical Topcon solar cell, initially it will not show any degradation with UV, although the damage is happening. But at a certain damage, it actually becomes sensitive, and then you see it picking up. Corrosion is a good one as well. So corrosion, it has to corrode through the contact to the interface, and then it's when the most damage happens. So initially you would not see anything because the line resistance actually doesn't increase that much. But then once you hit the interface, then boom, you see a massive uptake. So unfortunately, they're not linear. And yeah, like the top companies, and I would like to applaud SunPower again. They've done excellent work in this area, and they've been and they had excellent results. So they were happy to share that at the many conferences. But yeah, they were definitely an inspiration for everyone. Yeah.
All right, we have another question. Is there any other hypothesis on where the chlorine ions could be coming from other than the flux?
Yeah, so floating PV would be the most obvious one, but then also a lot of contaminants unfortunately contain most of the periodic table. So like I live in Sydney, quite a clean city, but I live close to a road, so there's a lot of soot coming onto my balcony, onto my solar panel, so that contains chloride. So there's always opportunities for it to come in. It's also a common contaminant if you have contamination like fingerprints. So there's many different sources, unfortunately, and in post-mortem analysis for off-field modules, people often find significant amounts of chloride. But yeah, it's indeed also the solar influxes. It's quite amazing what elements we identify there once we do analysis. So that's not everything is on the spec sheet. So, and that's something we're working on. And additives, yeah, that's also something we're still working on. And the additives for the encapsulants, yeah, you don't always know what's in there. Yeah, but the solar influx would be one of the definitely halogens in there. Yeah.
Okay. All right, for Topcon back contact modules where manufacturing processes is different, same degradation patterns arise, or are they different degradation issues?
Yeah, we haven't looked at those in detail. But yeah, you would use the metallization is quite different there. If we look at yeah, of course the sun power Maxion of the Maxion solar cell is a Topcon back contact solar cell, so with poly contacts for both hole so hole and electron. But there's copper metallization, so that would be different. The features would also look different because, of course, you have the contacts; they're interdigitated, so the signature would definitely be different. But I would be keen to look into that as well. Yeah, but yeah, you would be. Yeah, so that contact, of course, you care a little bit less about bifaciality. So you would, yeah, you probably apply more metal there or cheaper metal. Yeah. Different pace.
All right, next question is, given the rapid commercialization of Topcon and HJT technologies, what is the new regime are being proposed to address the emerging failure modes?
Yeah, so that's a very good question, and it's something we're working on as well as part of. We're involved in some of the IEC committees and semi committees. It would be typically multi-stress test because we see, for example, if corrosion is happening, we see that the adhesion of the contact is compromised. So, like thermal cycling, so preceded by a damp heat test would make sense, or to do multiple stressors at the same time. So NREL is doing some great work there. So Dirk Jordan's group, and we're also working on that. So it would like to be a combination. There's also, we can go hotter for damp heat. So for 95, you probably if you do 95, 95, that would speed it up at least by a factor of 2 or even more. So yes, we're working on this, and I know the IEC is and all the standard agencies are working on this. Yeah, but it would be typically a combination of multi-mode, multi-stressors, because we see unfortunately they're correlated. Like PID is another one. PID brings sodium to your solar cell. So of course, then if you do damp heat, you would expect it to behave differently if you bring significant sodium, even if you don't have a like, and we know we bring sodium because we have PID. So the Topcon solar cell is sensitive to PID, but then if you put it in, if you illuminate it, then that PID effect is mostly gone. So, which makes sense. So there, you would actually say you need a multi-stress test because, yeah, testing solar cells in the dark for PID doesn't make sense because they only have a voltage when they're illuminated. But then there is clearly sodium there because you had a response in your PID polarization. So can that actually lead to corrosion damage? So a PID followed by damp heat, and PID testing is only 200 hours. So that would definitely be a good one. But yeah, it will be either combination of tests or where you do multiple stressors at the same time, and that's something we're also doing research on.
Got it. That makes sense. All right, this one is what the people are wanting. Which one is better, in your professional opinion?
Yeah, that's. I think both of them can be made stable enough. Like Sanyo, Panasonic, they pioneered heterojunction. These solar cells are among the best, or these modules were among the best that we've seen ever in our testing. Of course, they were very conservative in the bill of materials. So I would say the cells are sensitive. So also, like heterojunction solar cells are sensitive, and Topcon solar cells are sensitive to certain failure modes. You just have to ensure that your bill of materials and how the bill of materials would progress over the whole lifetime, that protects the cell. Because in principle, the cell, if the cell doesn't see the stress factors, it will behave. So I cannot make a generic statement there. So both technologies can be made stable. The main message of my presentation is that these cells are different than PERC. So for all the listeners, so don't treat them the same as PERC. Don't expect them to be as forgiving as PERC. Like we try to test PERC a lot in our lab, and they're just so forgiving, but then we don't see the same for Topcon. So treat them more delicate and heterojunction as well. And then, of course, we have to make them more intrinsically stable, because that will allow us to go to cheaper bill of materials. So that's basically the message. But yeah, there's also probably many Topcon, some power modules out there that are still working fine after 10, 20 years. I'm not sure when they implemented Topcon in their cells, probably 2015 or something. So you would be able to find modules that are 10 years old with Topcon contacts. Yeah.
And just to clarify, in that answer, you mentioned being conservative in the bill of materials. We don't have much time yet left, but would you dive into what that means to you?
Yeah, basically, so there's now because there's such a price pressure. So in the US, of course, with IRA, you have with the IRA, you have a slightly higher cost base than in China at the moment. So China, like the spot market prices are close to 10 cents per watt peak. Just think about that. 10. So a lot of companies are moving to EVA for Topcon as well, which is so to save cost. Yeah, so to move away from PUE is quite expensive. So be conservative is basically, going a little bit, like getting a higher quality, lower water vapor transmission rate than you might want to do from a cost drive. But the cost pressure is relentless. So I fully understand that, but just it may have negative consequences.
Got it. Okay, well, we are just out of time, but I want to thank you and Niklas for the lovely and educational presentation. Thank you guys so much.
Okay, thank you.
Pleasure.
Visit Sinovoltaics.com to learn more.